Hello everyone, this is the first review of Unit 3, Exam 3 review, Chapter 25 and 26. Chapter 25 is mainly about induced current and induced EMF. Main points, learning objectives are understanding circumstances under which change in magnetic fields lead to induced currents, understanding how the movement of a conductor through a magnetic field leads to emotional EMF, use Lenz's law and Faraday's law to determine the direction and signs of induced current. So if you have some ideas about these, you are on a good standing. Chapter 26 was about understanding relationship between AC currents and AC potentials in resistors, understanding how electrical power gets to and is used in homes, and understand the circumstances under which electricity can be hazardous to human and safety systems. I'm going to start with motional EMF. We talked about how if we move a conducting wire or conducting sheet through a magnetic field, there will be charge separation in it because of the magnetic forces pushing charges. Using right hand rule 3, we can see here that we have put our fingers first along the velocity, remember, and then we curl our fingers towards the magnetic field, which would be into the board here, and your thumb will show the direction of the force applied to positive charges. So positive charges will be pushed in this direction, negative in that direction. As you see here, they will be accumulated in this fashion. As the charges accumulate, there will be electric field generated, because if there is a charge separation, plus minus charges, there is always electric field generated from plus to minus. That's a Unit 1 topic. So a little bit of review for the final. And this electric field will stop the charge separation after a while, because it will have forces applied to charges upwards, electric forces, downward. Electric forces will be downward, and magnetic force, as we said, will be upward. They will maintain a balance a bit later, and it will stop. But we will have a battery that we can use, connect to a system, and generate a current in this fashion. This is what motional EMF was. And calculating what it is pretty simple matter. We'll use epsilon for EMF, motional, or other ways we generate induced EMF, and this epsilon is the symbol. I would like to call this induced or motional. And it's equal to the speed that we move the conducting wire, the length of it times magnetic field. As simple as that. On this page here, what we're seeing generally, if we generate motional EMF, which is a voltage, generated voltage simply at the simple level, we can connect it to a circuit and we can generate a current, and that will be an induced current here. And we can connect this to a system, light up a light bulb, for example. If we put a light bulb here, we'll have an internal resistance. So we'll have a simple circuit that we can use this as a current. And we can calculate that current if we know the induced EMF or motional EMF. We calculate this, and then if we know the resistance of the system, we can calculate the current using this law, which is Ohm's law. Remember, Ohm's law is equal to I is equal to delta V over R, and now delta V is epsilon, motional EMF. This is something we knew, and we can apply it here from Unit 2. If I am pulling a wire to maintain its motion at constant speed, we should have equal and opposite forces. So we should apply a pull force that is equal to magnetic force. Once the current is generated in this wire, we will have the magnetic force to be equal to the current times the length of it times the magnetic field. This is from Unit 2, and the pull force will be equal to that. Another thing we can calculate from Unit 2, we know that power dissipated across a resistor is equal to current squared times R. We can use that to calculate what is the power dissipated. This second part was about mainly magnetic flux and how it changes and can also induce EMF and current. So first we talked about what is magnetic flux, and the best way to imagine it is to assume you have a loop like in here, and air is blowing through it or water is flowing through it, and the tilt of the loop and the area of the loop will matter how much water is flowing or how much air is blowing within the loop. And magnetic flux is very, very similar to that. We learned about magnetic field lines in Unit 2. So if we have a magnetic field in a region and we're interested in how much flux through a loop in that region, we look at how many magnetic field lines are passing through it simply. And equation wise, this is how it is found. It depends on the strength of the magnetic field. If the magnetic field is strong, we will be having more closer lines in here, if you folks remember. It depends on how large the area is, and it also depends on what is the angle between the normal to the area or axis of the area. Let me rewrite that. And the magnetic field. For example, in this picture here, if I put my area in a fashion that its normal is parallel to magnetic field, there will be the most number of magnetic field lines passing through it. If I put my area where its normal perpendicular to magnetic field, area is flat here, magnetic field is just going above or below it, no flux through it, so flux will be 0. If I tilt the area, flux will decrease, but it will not be 0. If I have one loop, here is my flux, BA cosine theta. If I have more than one loop and loops, I'll just multiply that equation by the number of loops, because each loop here will be having a flux through it, and we'll add all those fluxes. So that's what magnetic flux is. And Faraday law tells us if there's magnetic flux change through a loop, there's an induced EMF and induced current. We'll use Faraday's law to calculate the magnitude of that induced EMF and induced current. But we'll use Lenz's law to find the direction of induced current. Lenz's law tells us that there's an induced current in a closed conducting loop if and only if magnetic flux through the loop is changing. The direction of the induced current is such that the main part of the Lenz's law, as the first part is actually Faraday's law, the direction of the induced current is such that the induced magnetic field opposes the change in the flux. So induced magnetic field doesn't want to change. If the flux is increasing, it will be opposing the background magnetic field. If the flux is decreasing, it will be in the same direction of the background magnetic field. That's the main point here. We will first find the direction of induced magnetic field, and then we'll use right-hand rule 2, this little picture you see here, to find the direction of current induced in the loop using the direction of induced magnetic field. Right-hand rule 2, again, we roll our fingers along the current and open our thumb. Thumb will be showing the direction of magnetic field, and the fingers will be showing the direction of current. We'll be doing this kind of backwards here. We will know the induced magnetic field. This will be induced here. So we'll put our thumb along that field and roll our fingers. That's it. We'll see the direction of the induced current. How can our flux change? We kind of reviewed this in the previous page, but let's review this again. 1, it could be the magnetic field is changing. In this picture, for example, I have this bar magnet here. If I move it closer to this loop here, magnetic field increases as we go closer to the bar magnet, right? We all know this. So this will be moving in towards the loop. Magnetic flux will increase because magnetic field will increase. If magnetic field increases, magnetic flux increases. That's one way to increase flux. Another way is that background magnetic field could be constant, like in here, but I change the cross-section area by squeezing my area. Let me put the flux equation here. So we can also think about this mathematically. It's the area times the magnetic field times cosine theta, angle between theta being angle between the magnetic field and the normal of the area. So in the first one, my B is changing, flux is changing. The second one, A is changing, flux is changing. We can also think in terms of mathematical approach. Another way to change, the third way to change the flux is to change the cross-section area's angle with angle of normal, not at the area itself, with the magnetic field. So this is my normal here. Here I have a tilted normal, have an angle. Here I have my normal. In this case, you can imagine this is my area here. Magnetic field is parallel to the area, perpendicular to the normal. Please keep in mind that it's very common mistake to take the area instead of normal. But the angle we are interested in between the normal and the magnetic field. And normal is always perpendicular to the surface area. So in the first case, I have a lot of magnetic field lines passing through my area. This is the maximum flux again, as we've seen in the previous page. So a lot of lines because the normal is parallel to the magnetic field here. Normal is downward, magnetic field is parallel, and a lot of magnetic field lines passing through the area. If the normal is parallel to magnetic field, the area itself becomes perpendicular and a lot of lines passes through it. The second one would be medium, we have an angle, and the last one would be minimum or zero flux because normal is perpendicular to magnetic field here. And the area itself is parallel, so no line is passing through. Keep that in mind. So three ways of changing the magnetic flux: changing the magnetic field, changing the area itself, or changing the angle between the normal to the area and magnetic field. All those will cause an induced EMF and thus an induced current in the system. What we use to find the direction of induced current is Lenz's law. Our background magnetic field will always oppose the change. Our induced magnetic field will always oppose the change. Background magnetic field is increasing, induced magnetic field is against that. Background magnetic field is decreasing, induced magnetic field will be in the same direction as that because it doesn't like to decrease as well. I have to understand how to find the directions. Actually, finding the magnitude of induced EMF via Faraday's law is pretty simple. Change in flux divided by how much time it takes to change that flux. So the rate of change of flux, this is change in flux. So we're going to calculate the magnetic flux, look at the change in it, and look at how much time it takes to change that magnetic flux. We'll divide them, we'll find the induced EMF. Notice the absolute value here. We don't really care about plus minus because we will decide the directions using Lenz's law. And it's the easier way. And this guy is, of course, induced EMF. If we have one loop, it will be this equation. If we have two loops through which flux is changing, we'll multiply it by the number of loops. This is the number of loops here. After that, if I have an induced current which I'm using to calculate induced EMF, which I'm using to generate a current through a resistor system, Ohm's law, as always, holds. Current is equal to potential difference divided by the resistance, and our potential difference is epsilon here. How do we define the direction of the current? Induced current is Lenz's law. That's our setup here. It's pretty easy to make mistakes in finding the direction. So I put here several examples, and for each of them I'm gonna go through one or two. I'll let you go through the others. I'm gonna post the answers later on as annotated lecture notes. Please practice them yourself and check the answers on the annotated version of this lecture. So the question here is, what is the direction of induced current in each case below? This guy here is a little fuzzy, sorry about that, but it's understandable. Going to left here, I'm thinking about this loop over here. As you see, there is a loop on the left, and look at the area of the loop. Area. This loop that starts here, goes around and comes back there. Area is decreasing, right? And that means my phi is decreasing, the flux is decreasing because area is decreasing. We put the flux equation again over here. Area times magnetic field times the cosine of the angle between the normal to the area and magnetic field. Over here, magnetic field is out of page. My flux is decreasing because area is decreasing. My loop will not like that. B is out of page. B induced. Let me put my B induced red. B induced will also be out of page to stop that decrease and go back to where it was. It doesn't like that change. So B induced here will be out of page. The same direction as the background magnetic field, because again, background flux is decreasing and my loop doesn't like it. After I find that, I use my right hand rule 2 to find the direction of current. I should grab this loop here and my thumb should be out of the board. I'll try to draw that. It won't be easy, but hopefully it will give you an idea of how I should curl my fingers. These fingers are curling in this direction and my thumb is out of the board. This is my B. Imagine this is out of the board. And this is the current, induced current. So the induced current should be in this direction. Please practice yourself with me here. It's very hard to draw, but that's the induced current. This one is going out of a magnetic field that is out of page here. What is happening here is that area inside the magnetic field is decreasing. Let me go back to blue here. So I'm going to show my induced magnetic fields and currents in red. So because it's going out, area is decreasing. Because of that, flux is decreasing. If flux decreases, B is outside of board, out of the board, or out of the screen, then B induced will also be out of the screen. Oops. This is Lenz's law. Then I'm going to my right hand rule 2. Induced magnetic field inside this loop is out of the screen. The same thing here, right? I'm going to roll my fingers along the I'm gonna put my hand in a way that my thumb is out of the screen. Imagine this is out of the screen, and when I roll my fingers, here's how they will roll, right? And I will have my current in this direction. Please try all the rest. I'm going to post the solutions. I'm going to show you in this current direction, in this magnetic field direction. You'll find the rest. I forgot to mention this part over here. We kind of touched base on this. There is only logical solutions. There might be find in the direction of induced current and so on using Lenz's law. We won't be doing any calculations. This is eddy currents. So if we move conducting wires in magnetic field, there's induced current in them. If we move conducting sheets, there's also induced current in them. But they're kind of random currents that forms full circles, as you see in this picture. And we can't really calculate them, but we can find their direction using Lenz's law. Let me see what we have here. We have magnetic field down, right? This sheet is moving right here. So on the right side here, magnetic flux is decreasing. Flux is decreasing. My magnetic field down. So my induced magnetic field should be down on this side here. Because this side is going out of the magnetic field area, flux is decreasing. And if I use right hand rule, my induced current on this side will be in this direction as shown. Try the other side yourself. It's just going in. Flux is now increasing down. This guy doesn't like it, and magnetic field, induced magnetic field should be up to stop that increase. Right? And we'll have current in this induced current in the opposite direction fashion. These two sides of the sheet actually work as if we have in same I always forget this word. Same poles of two bar magnets, so they push on each other, which is why we have, when we move the conducting sheet through magnet, you played around with this in lab, but we didn't really talk about it a lot in lecture. When you move a conducting sheet through a magnet, it's pushed because of that. But all we need to know here is what we already know, how to find induced current direction if we know what's happening to the flux. And we use Lenz's law for that. Two more examples here. I'm going to leave up to you folks. I'm going to solve one that is interesting here that might be hard to understand because we didn't talk about rheostats. And the rest, again, I'm going to put the solutions. Please look at the solutions and practice them yourself. Here we say we have a rheostat and setting is being changed. Rheostats are adjustable resistances. That's all. We didn't really talk about them, but it's not too much to talk about. If I move this way, that means I am decreasing resistance here because I'm going to use another color here. Because the amount of resistance in my resistance in my circuit changes. I'm leaving this part out and this part is only in. So the bottom line is when I move this rheostat to the left in the circuit, R is changing, R is decreasing. Okay? And the question overall asks what is the direction of induced current? In all the cases below. So if in this circuit R is decreasing, what happens is that we have a power source here, right, delta V. It will generate a current here in this fashion, plus to minus. Plus to minus. Am I seeing this way? It's in there, shown in the other direction, but we'll use the plus to minus here. Let me redo that. So in this loop here is my current. This is I. We are not at induced current yet. So I have a circuit here. There is a direction of current, and resistance in that circuit is decreasing. Right? What happens to the current? Ohm's law. I is equal delta V over R. resistance decreases, inverse, current increases. So this current is increasing here. Let's find the direction of magnetic field in this first loop here using right hand rule 2. Let me try it over here. So I'm gonna roll my fingers along the current. It should be something like that, right? I have to learn how to draw a nice hand. When I roll my fingers, it will be something like that, because that's the direction of my current. And as I do that, if I open my thumb, imagine this guy is into and out of the board, okay? That's how they are trying to show it here. My thumb will be in this direction, right? If I apply it to what I see there, over here, it's hard to draw fingers into the board, but I'm trying to show you here the right hand rule. If I apply that to here, roll my fingers along there, which is the direction of current. I'm going to use yellow for the roll my fingers along here, I open my thumb, it will be that. So that's the direction of magnetic field here. That's the background magnetic field. What is happening to this guy if current increases? It also increases, right? And let's remember, this is topic of unit 2. B here is equal to mu 0 I over 2r, the radius of the loop. If I have more than one turn, I also multiply by that number of turns, but we have one turn here. So B is increasing. B is to the left, flux is to the left. That B goes through this guy as well, right? There's a flux because of that B through this guy. B increases, flux increases through it. Flux increases through it, the loop will not like it. It will generate a background magnetic field in the opposite direction. So we'll have a B induced through this loop to the right, right? And using right hand rule, I'm going to curl my fingers while my thumb is to the right. This will be the direction of induced current. You can say, looking from the left, it's clockwise, right? Alright, do all the rest. This one was the more interesting one. We didn't talk about rheostats, but the rest are something we always talked about. First one, I move magnet towards here. What happens? What is the direction of current? You can think in terms of down in the front or up in the front. That will do it, and I'm gonna post the answers again. So I'm gonna show induced magnetic field and induced current directions for all of those. Another one here, I'm passing these. This one could be interesting to look at here. Area is increasing. You see the arrows there? They are increasing the area. Area increases, flux increases, right? Flux increases, induced magnetic field will be opposing the background. These dots means background is out of the board. Induced magnetic field will be into the board. Right hand rule 2 will tell me the current will be in this direction. Please again practice these with right hand rule 2. So I induced. Clockwise again. This question is a very nice question involving a lot of stuff. That would be on the hard-end questions I might ask you. I'm going to quickly tell you how to solve it. I already gave you the answer. Please solve it. Get the answers. If you're still confused, talk to me, okay? The direction of induced current is already given, but if I ask you the direction in the exam, of course I won't give it to you. We'll discuss it though. We'll again talk about why that is the direction. The question says that we have a solenoid here that passes a current, and there is a magnetic field through the solenoid. from the right hand rule too, I can find the direction of current in the solenoid. Let me use blue for that. Right? Solenoids works the same as the loops. I'm gonna roll my fingers along the current. My thumb should be the direction of magnetic field. Here is what I would do here. The current would be down if the magnetic field is to the right. Alright, the solenoid has 1200 turns, so that's N, 1200 number of turns. A diameter of 2 centimeters. I'm going to put the radius because we are generally interested in radius. 1 centimeters. I'm converting the meters right away. And the length L is 7.5 centimeters. 0.075 centimeters. The resistance of the loop is 0.02 ohms. So this loop here has a resistance along. I'm going to represent it like a resistor along it. And that resistance is, maybe I'll put the loop values here. 0.072 ohms. If the current in the solenoid is increased by 1.4 ampere in 30 milliseconds, we're increasing current, and there's a current change, 1.4 amperes, and the time is 30 milliseconds. That's 30 times 10 to minus 3 seconds. What is the induced current in the loop? Now, as I do my thinking, I'll say, okay, induced current should be caused by an induced EMF, and I can find it in the loop using Ohm's law. That will be epsilon induced divided by R. That would be replacing my delta V here. So if I find the epsilon induced, I am good. How do I find it? Epsilon induced from, due to the change in the solenoid, will be N times delta phi over delta T. I know delta T, so all I have to do is find delta phi. N is 1. That is the number of loops here. I'm looking at induced EMF on this guy, and the number of loops is for that guy, not the one that the solenoid we have here. How do I find delta phi? I'm gonna find delta B. Apparently the B is changing. B is changing because current is changing here, right? I'm gonna find delta B, and I'm gonna say delta phi is equal to A times delta B times cosine 0 in this case, because notice this is my area. This is the magnetic field passing through it, background magnetic field, right? And its normal is parallel to that. That's normal to the area. So theta is 0. And I can directly find delta phi using that. Remember, we did some examples in here. So I'm going to find my delta B, put it in there, and then I'm going to find my delta phi, put it in here, and when I get my epsilon induced, I'll have my I induced. How do I find delta B? I'm going to write down the magnetic field equation for a solenoid. Mu 0 N I over L. Now, if I know that there's a change in the current as 1.4 amperes, yes, that's what's supposed to be on this side, by the way, with the solenoid. Change in current, that's not in the loop. I can directly calculate my delta B using change in current, right? Mu 0 and delta I over L. So we are now ready. Insert this guy here, get delta B, insert this guy there, get epsilon induced, insert that guy there, get I induced. The values are given to you. I induced should be 1.4 10 to minus 3 amperes. That's about 41 milliamperes. Amperes to milliamperes we convert there. Let me also give you what I found for each of these values. Please work through it yourself. For delta B, you should find about 0.03 Tesla. 0.028 to be exact, so around there. And you insert that in for epsilon induced, you should find about 0.03 volts. Interesting, isn't it? And I induced as given will be 4.1 times 10 to minus 3 amperes. You can convert to milliamperes by multiplying by 1,000. There's a mistake here, I think. 4.1 times 10 to 2, which should be 10 to minus 2, yeah. 10 to minus 2, let me correct that. 10 to minus 2, and it should be multiplied by 1,000, 10 to 3 should be about 41 milliampere. Alright, this is getting long already. I'm gonna move quickly here. For the alternating current, all I want to remind you is we're looking at the average values. They actually vary over the time, but either we're talking about the peak values here or average values, what we call RMS, root mean square values. The rest will be the same. We will use the Ohm's law, we will use the power equation to calculate. As we know, all the equations from unit 2, power is equal to I squared R, or delta V squared R, only we'll be using average values overall. If we are only asked, if it's not specified in a question, we'll assume that's average value. If we are only asked, we'll find peak values using these equations here. These are peak values. And we only cover simple resistance circuits, not the rest, so it will be simpler level coverage. Another important thing in this part was transmissions, how we use them to increase the voltage as we carry the power in our homes, and that will help us to lose less energy and then decrease them here. And we had simple equations for transformers. So here is one related number of turns with the potential differences. Here is one relating currents with the potential differences. I want you to use these to get to what you're looking for. We also talked about how human body can be represented as a circuit, and the current will be choosing a way to go in any direction it can, and we will always have series circuits. Keep that in mind as well. I'll quickly tell you about this question. This is about transformers. It says a power pack charging a cell phone battery has an output 0.6 ampere and 5.2 volt, put in both in RMS. What is the RMS current at the 121 volt wall outlet where the power pack is plugged in? Power packs, chargers are all transformers, so I will represent the transformer here quickly. What you have to do with the transformers is to decide what is the primary, what is the secondary. One good clue is that primary is always at the wall. V1 is 120 here. That's how we represent the transformers. And we are charging a cell phone here. So we will have V1, I1, N1, N2, V2, I2. In this one, you're given V2 as 5.2 volts, I2 as 0.6 ampere. to find I1, and you're given V1 as 120 volt. That's all. Number of turns are not involved, and you're gonna use V1 I1 is equal to V2 I2. Simple as that. And this should be your answer. Work it through and make sure you find the answer. Alright, that's it, my friends. I'll see you in the next